Great. Well, it's my great pleasure to introduce Jacob Lurie from Harvard, who is going to tell us about Bezout's theorem and nonabelian homological algebra.
Thank you. It's my great pleasure to be here. This department has a lot of energy in it. So my subject is the theory of what's called derived algebraic geometry, which, roughly speaking, is what you get if you take the foundations of ordinary algebraic geometry and jazz them up a little bit by inserting some ideas from homotopy theory. Before I get to that subject, I'd like to begin with something very classical that will hopefully motivate why the foundations of ordinary algebraic geometry need to be jazzed up. So I'd like to begin by thinking about Bezout's theorem. So what does Bezout's theorem say? Well, consider the complex projective plane. And suppose I give you two smooth plane curves in the projective plane. So these curves are defined by polynomial equations which have particular degrees. Let's say C is a curve of degree n, and C prime is a curve of degree m. So in its simplest form, Bezout's theorem tells you that if C and C prime meet transversely, then the number of points of intersection of C and C prime is equal to the product n times m. So let me just reformulate this statement a little bit using the language of cohomology. C and C prime are smooth curves in the plane. In particular, they are smooth manifolds, and they have fundamental classes, which you can identify with elements in the cohomology ring of CP2. So I'm going to let C in brackets denote the fundamental class of C, and C prime in brackets denote the fundamental class of C prime. Then the product of their fundamental classes, that's this number n times m. And what are we saying? Well, we're saying that that's equal to the fundamental class of the intersection of C and C prime. This is a zero-dimensional manifold. And taking the fundamental class in that case just amounts to counting the number of points that that manifold has. So in some sense, you should regard this equation of fundamental classes as obvious. Because what is the product on cohomology supposed to do? It's supposed to intersect things. So that might make you think that this is obvious, but it can't be completely obvious because it's not necessarily true. It's true if C meets C prime transversely. But if C and C prime do not meet transversely, if they're tangent at one or more points, then in fact this is always false. The number of intersection points of C and C prime in that case is always smaller than the product n times m. Why is that? Well, it's because when C and C prime meet non-transversely, you don't just want to count the number of points of intersection, you want to count them with the appropriate intersection multiplicities. So in the non-transverse case, you want another formula of this kind, but where you do something less naive for the left-hand side here, where you count points according to multiplicity. So let me talk a little bit about how you get those intersection multiplicities. So let's suppose that C and C prime are contained, instead of in the projective plane, that they're in the affine plane for simplicity. So the affine plane, on the affine plane, we can choose coordinates x and y. And then we can write the ring of functions on the affine plane as a polynomial ring in the variables x and y. And now C and C prime are defined by polynomial equations. So C is defined by the equation f equals 0, where f is some polynomial in x and y. And C prime will take to be defined by the equation g equals 0. So if we want to think about the ring of functions not on the entire plane, but just on the curve C, well, we should take functions on the entire plane and then remember that on the curve C, the function f is equal to 0. So if we divide out by the function f, we get the ring of functions on the curve C. Similarly, if we want the ring of functions on the curve C prime, we should divide out by the element g. So the ring of functions on C intersect C prime should be something like this polynomial ring, but divided out by both the defining equation of C and the defining equation of C prime. So this is the ring of functions on C intersect C prime, where the intersection is interpreted scheme theoretically, not just set theoretically. So if you don't know what that means, well, roughly speaking, it just means we're not interested only in the points where C and C prime intersect, but also in the rings that come up when we impose the defining equation of C and C prime. And it turns out that the rings which come up remember more than just the number of points where C and C prime intersect. So let's consider some examples. So first, let's consider the example where C and C prime meet transversely at the origin. So let's say C is the line where x equals 0, and C prime is the line where y equals 0. Then functions on C intersect C prime would be like taking this polynomial ring in two variables and setting both of the variables equal to 0. And in this case, you just get the complex numbers, which is what you expected. That's the ring of functions on a single point. And the fact that it's just one point is reflected in the fact that this is one-dimensional as a vector space over the complex numbers. So let's consider a slightly more complicated situation where C and C prime do not meet transversely. Namely, let's suppose that C is again given by the equation, the line where x equals 0, but that C prime is given by a parabola defined by the equation x equals y squared. So here's the curve C, here's the conic C prime, and they're tangent at the origin. So this is a non-transverse intersection. What happens on the level of rings? Well, the intersection of C and C prime is encoded at the level of rings by taking this polynomial ring in x and y and killing x and x minus y squared. Well, of course, once you've killed x, you're then just killing, in addition, y squared. So this is the ring C adjoin y modulo y squared. And now this is not naively what you would think of as the ring of functions on a point. It's a little bit bigger. It's two-dimensional over the complex numbers. And what that's reflecting is that this is a point of tangency. And that, in fact, you really ought to be counting this point as being multiplicity 2 in the intersection of C and C prime. So what's true, then? Well, in general, for plane curves, the product n times m is equal to the number of intersection points counted with their multiplicities. So we can write this as a sum over all points which lie in the intersection of C and C prime of an intersection multiplicity, which, according to the prescription which I've described here, is given by the dimension of a certain ring. You want to take the complex dimension of the ring of functions of the intersection at that point. How do you get that ring? Well, you take the ring of functions of the projective plane, and you impose the defining equations of C and C prime simultaneously. So in algebra, we can write this. What we're supposed to be doing is taking the ring of functions of C and tensoring it with the ring of functions of C prime over the ring of functions of the projective plane. And I'll write a little p here to denote that this should all be happening really locally at the point P. So this dimension what computes the intersection multiplicities, and if you add them up, then you get the product n times m. This is a more sophisticated version of Bezout's theorem, where the curves don't have to intersect transversely. So you might ask at this point, why are we considering only curves in the plane? Let's consider something a little bit fancier. Suppose that C and C prime are varieties of dimensions A and B. And suppose that they're contained in a projective space of dimension A plus B. So generically, you'd expect that they intersect in finitely many points. Now, two subvarieties of projective space of any dimension, you can still associate a degree. So let's suppose that C has degree n and C prime has degree m. Well, once again, if C intersects C prime transversely, then the number of intersection points of C and C prime is just given by the product n times n. That's exactly what you would expect. What if C and C prime do not meet transversely? Well, once again, there's still a formula like this, but you have to consider points with the appropriate intersection multiplicities. But in high dimensions, extracting the correct intersection multiplicity is not as trivial a matter as it is in the plane. It's not just given by the dimension of this ring. So to understand why that is, I want to consider sort of some degenerate cases of this sort of situation. So let me suppose that C is given by a single equation. It's given by setting f equal to 0. And let's suppose that C prime has a ring of functions R. So what is our prescription over here for finding the intersection multiplicity? What we're supposed to do is take the ring of functions of C prime and then intersect by imposing the defining equation of C. So that means we're supposed to take R and divide out by the function f and then count the dimension of this ring. So we can identify R mod f with the co-kernel of the multiplication by f map from R to R. Now let's consider a special case, which is not really applicable to our situation, where R is finite dimensional. So if R is finite dimensional, multiplication by f, we can think of that as just some linear transformation on a finite dimensional vector space. It's given by a matrix. And you might think that, generically, if f is chosen at random, that matrix is probably invertible. It probably has non-zero determinant. And in that case, the answer is just going to be 0. But of course, this is not necessarily the case. For some degenerate f's, its determinant might be non-zero, in which case this thing would be positive dimensional. And in fact, as f sort of wanders over the space of possible n by n matrices, the rank of the matrix can jump, and the size of the co-kernel, the complex dimension, can vary. And this isn't what we want, because an important thing about intersection multiplicities, in some sense the defining property of intersection multiplicities, is that they don't really change if you perturb the situation a little bit. Another way of saying why in this case, where we have a parabola and a tangent line, we said this is intersection multiplicity 2, and we computed that algebraically. But just geometrically, you can understand why it should be intersection multiplicity 2. Because if you poke the line a little bit, you can make it intersect the parabola transversely. And if you do that, you see that that one point of non-transverse intersection perturbs to become 2 points of transverse intersection. So really, these intersection multiplicities are determined by the fact that they don't really change when you perturb the situation, and in the case of transverse intersections, the multiplicity is 1. But if we just want to extract these multiplicities by taking some kind of co-kernel of a matrix and counting the dimension, that doesn't look like it's very invariant under perturbations. As you perturb a matrix, its rank can change. But the observation that I want to make, in this case, the generic or the transverse case is where f has non-zero determinant, and so this co-kernel is actually 0. So the answer we expect in this case is 0. And if we just think about the co-kernel, we don't necessarily get 0. But whenever an n by n matrix has co-kernel, it also has kernel. So in fact, if we look at the dimension of the co-kernel of f, thinking of that as sort of the first approximation to what we want, and then we subtract off the dimension of the kernel of f, well, it's just linear algebra that we'll get 0. Now, of course, you might say, this isn't very interesting. Why am I going through all of this just to define something which is always 0? The answer is, well, this is very special and very degenerate because I'm saying that R is finite dimensional. But in more realistic situations, when we're actually intersecting these curves, it will often happen, or it does happen when we're intersecting curves, that R is infinite dimensional, but the kernel and co-kernel of multiplication by f are both finite dimensional. So in that case, this number is still defined, and it turns out to be more interesting than considering either the dimension of the co-kernel or the dimension of the kernel individually. It's somehow more robust or more invariant under perturbations. But of course, this discussion has all been very special to considering the case when C is given by a single equation. But the idea that somehow there's this naive approximation to the answer, and then there are some correction terms that you should add if you want things to be invariant under perturbations, is actually very general. So let me review for you a little bit of algebra, namely the existence of what are called torsion product functors. So let A be a commutative ring, and let M and N be A modules. Then you can define some new A modules, which are called tor I over A of M with N. And these have the property that tor 0 over A of M with N is just the tensor product of M and N. And these higher tor i's, although I won't review the definition, there's some kind of correction terms that sort of help you out when this naive tensor product is behaving badly on its own. So in many situations, considering the tensor product alone turns out to be a bad idea, but considering all the tor i's simultaneously will somehow fix that up. So with this in mind, let me state a fancier version of Bezout's theorem that works in high dimensions. So have I erased? So let C and C prime be contained in projective A plus B space. Remember that C is dimension A and degree n. C prime is dimension B, degree m. Then n times m is equal to, well, it's the number of intersection points. I'm going to assume, I should mention, that C and C prime meet in only finitely many points. But I'm not going to assume that they meet transversely. That's the whole point. I can compute the right intersection number by adding up the intersection multiplicities at all the points of intersection. But now the intersection multiplicities themselves, so I should credit Serre for this probably. The intersection multiplicities at the point themselves are given by Serre's intersection formula. they're given by a sum of contributions from these different Tor groups. So it's an alternating sum, -1 to the I, times the dimension of the group Tor I of the ring of functions of C with the ring of functions of C prime. So what is this saying?
So what does that say over the Tor to the
Tor I over the ring O of projective space. Sorry, this is probably invisible to the camera. And that probably didn't help, but so what is this saying? Well, if you look only at the term where I equals 0, the Tor group here specializes to just a tensor product. And what we're doing is saying take the ring of functions on projective space, impose the defining equations of C and C prime simultaneously, and then count dimensions. So in other words, we recover this formula if we ignore the terms where I is greater than 0. But of course, we're not supposed to ignore the terms where I is greater than 0, or we'll get something which is false. So in general, you should include the dimensions of all these Tor groups. So this is good on the one hand because we get a formula which we can use and we can compute with. If we want to know an intersection multiplicity, we can write down our rings and try and compute these groups, and in some situations we might be able to do it. But it's a little bit bad from the point of view of this very conceptual looking formula over here. So this very conceptual looking formula, we want the product of the fundamental class of C and this fundamental class of C prime to be the fundamental class of the intersection. So if C and C prime meet transversely, that's true in the most naive sense. If C and C prime are plane curves and they meet non-transversely, then it's true if we interpret the right-hand side in a less naive sense. That is, we don't just want to take the set-theoretic intersection of C and C prime, but we have to take the scheme-theoretic intersection. We need to remember the rings of functions on the intersection. And of course, we have to take that scheme structure into account when we compute fundamental classes. We have to interpret this as something which measures the sizes of those rings of functions. But even if we think about the scheme-theoretic intersection of C and C prime, we can't interpret the entire right-hand side of Serre's intersection formula. The scheme-theoretic intersection will tell us about the Tor 0 terms which appear here, but these higher Tor i's are not reflected in the scheme-theoretic intersection. So what I'd like to talk about in this lecture is how to fix that problem. Namely, it's not good enough to think about this intersection set theoretically or even scheme theoretically, but maybe if we jazz up our notions enough, then we can put ourselves in a world where this intersection really does have all the information that we need to extract the right intersection multiplicity. So this is where derived algebraic geometry comes in. So to get an idea of what that world might look like, I'd like to begin with a very degenerate situation. So let's go back to basics and think about Bezout's theorem, curves in the plane again, and let's even think about the simplest possible case of Bezout's theorem, namely two lines in the plane. So if L and L prime are lines in the plane, then it's the easiest thing in the world. Two lines in the projective plane always intersect in exactly one point, except when they're the same. And if L and L prime happen to be the same line, then of course this formula over here will fail dramatically. The intersection of the fundamental classes of L and L prime, that would be one point, but that's nothing like the fundamental class of the intersection of L and L prime. That's just the line L again, and that has the wrong dimension. So what's going on at the level of rings? So once again, let's put ourselves in the affine plane, where the ring of functions is this polynomial ring in two variables over the complex numbers. Now if L and L prime are two lines in general position, then we might as well take them to be given by the equations where L is given by the equation x equals 0, and L prime is given by the equation y equals 0. Then what is the intersection? Well, the ring of functions on the intersection we're supposed to divide out by the defining equation of both lines, and we just get the complex numbers. And that's exactly what we want. It's one-dimensional. Everything works very nicely. But now let's consider what happens when L equals L prime. So that both of these lines are given by the equation x equals 0. So in that case, we're supposed to take a polynomial ring in two variables, x and y, and we're supposed to mod out by x and x. And what do we get? Well, we get a polynomial ring in one variable, and it looks like the ring of functions on a line. It doesn't look like it's the right dimension. In particular, we can't take its dimension. It's infinite dimensional over the complex numbers. And what went wrong? Well, we've taken a polynomial ring in two variables and imposed two equations, but the two equations were not independent. They're the same equation. And in classical commutative algebra, it doesn't matter whether you impose an equation once or impose it twice. It's the same ring that you obtain. So whatever world we need to be in, it needs to be a world in which dividing out by x twice is different from dividing out by x once. So how are we going to find such a world? Well, of course, we're doing algebraic geometry, so we want everything to be commutative rings in the end. But let's just think about a baby example of the same problem in the world of sets. Suppose I give you a set, which I'm going to draw on the board as a bunch of points. And suppose in my set, I have two elements, A and B, and I want to identify them. Well, of course, everybody knows that I can identify them by collapsing them to a single point. I can make a smaller set in which A and B have been identified with one another. But now if I'm a homotopy theorist, I might do something a little bit different. Instead of making a smaller set where A and B have identified, I might think about this set as a discrete topological space. And I might instead make a larger space by adjoining a path from A to B. Now this is in some sense an equivalent construction. Because to a homotopy theorist, this interval from A to B, that might as well be a point. It's contractible. So the space that we make is actually homotopy equivalent to the space that we made with more naive construction. What then is the point? Well, the point is that this is a construction that it's interesting to iterate. If you want to set A equal to B twice, you instead adjoin two paths from A to B. And this is now interesting because if we have two paths from A to B, we have a non-trivial path from A to itself. This space is not homotopy equivalent to a discrete space. It's got a loop. So this might seem a little strange to you, but I want to, if it does, I want to convince you that in fact this is maybe a good way to think about what homotopy theory is. So you're all familiar with the idea that if you have various kinds of algebraic structure like groups and rings, then it makes sense to give examples of this kind of structure by presentations. You give generators and you give relations. So you can also do this when there's no algebraic structure, when you just have sets. That is, you can take a set, you can make a set by writing down elements, those are your generators, and then writing down relations, collapsing some of them into the same point. But now, in homotopy theory, there's this notion of a CW complex, which just means a space which is built by attaching cells. So what does that mean? Well, you start by writing down some zero cells, that is, plunking down some points. And then you attach one cells, that is, you join the points, some of the points to other points by paths. Then you adjoin two cells, which means you pick some loops, say this loop here, and adjoin a disk that's bounded by that loop. And then you're allowed to proceed and attach cells of higher and higher dimensions. But the way I want you to think about this is you're really presenting a set by generators and relations. So the generators are the zero cells, the points. The relations are the one cells, the arcs that you add to join different points together. But you're not just thinking about generators and relations, but you're thinking about an incredibly sophisticated generalization of that, where you also think about relations between relations, like this 2-cell here, and relations between the relations, and so on. So that's how I want you to think about the world of homotopy theory. It's a generalization of the world of sets where you have generators and relations between relations, and so on. And what I'd like to get at is that this is an interesting thing to do, not just with sets, but also with other kinds of algebraic structures, like commutative rings. So derived algebraic geometry is based on the idea of doing classical algebraic geometry, but replacing commutative rings by something that simultaneously has the flavor of commutative ring theory and homotopy theory. The basic objects that you work with are going to be something that sort of a space and a commutative ring simultaneously. So there are a number of ways that you can try and make that precise, but for this lecture, we're only going to use the most naive of them. We're going to consider topological commutative rings. So a topological commutative ring is just what you might think it is. It's a topological space equipped with the structure of a commutative ring for which the ring operations, addition and multiplication, are continuous. So what are some examples? Well, here's a silly example. Let R be a commutative ring. Then we can take R and endow it with the discrete topology. And it becomes a topological commutative ring in a somewhat trivial way. So one thing to keep in mind about this business of using topological commutative rings is that we're really interested in these objects from the eyes of a homotopy theorist. Meaning we're going to regard two topological commutative rings as equivalent if they have, roughly speaking, the same homotopy type. That is, if we have a map from R to S of topological commutative rings, which induces isomorphisms on all homotopy groups, then we think of R and S as equivalents. And this map, although it might not be an isomorphism of topological commutative rings, it's somehow just as good as an isomorphism. Now, a consequence of this is that it's really hard for me to give you any interesting examples. I'd really like to give you a non-discrete example here to get your mind around, but it's difficult because although topological commutative rings occur all over the place in other areas of mathematics, the ones that appear are not interesting from our point of view. So for example, if you're an analyst, then you might like topological commutative rings like the real numbers, or the complex numbers, or various function spaces that form Banach algebras. But all of those are completely uninteresting for us because as topological spaces, they're contractible. So in other words, the real numbers and the complex numbers, those are equivalent to 0 in this world. On the other hand, if you're coming from algebra, then you might see a lot of topological commutative rings because you get topologies whenever you take a completion. So for example, when you make the p-adic integers, this has a p-adic topology. But as a topological space, the p-adic integers are totally disconnected. There are no non-trivial paths that you can write down in the p-adic integers. So from our point of view, that ring might as well be discrete. So if these aren't good examples, where are the good examples? What sorts of topological commutative rings do we actually want to work with to do algebraic geometry? Well, the answer is that they arise from doing certain constructions. So let's take, for example, this polynomial ring, functions on the plane, C adjoin x and y. And I'm just going to give it a discrete topology. And now suppose that, so here's a picture of it. It's just a bunch of points, one of which is y and one of which is 0. And now suppose I want to intersect a line with itself. In other words, I want to impose the equation y equals 0 twice. So if this was just the world of sets rather than the world of rings, I'd just attach two paths from 0 to y. But the problem is that the space that I make by doing that is certainly no longer a ring. However, I can always take the sort of free commutative ring that's generated now by those two paths. So you get a lot more junk in there because you can take sums and products of any points that lie along these paths. So the thing that you get is a big mess, and it's not something that you can really visualize geometrically at all. However, it's something that has good formal properties. It's good for doing algebra, as we're going to see in a minute. So let's return to this formula over here, this naive formula for the intersection multiplicities, which only counted the dimension of the Tor 0 term. So what I'd like to say is that the difference between this naive formula and Serre's embellishment of this formula, Serre's inclusion of these higher Tor terms, the difference is really that in this naive formula, you're taking the tensor product in the wrong world. You really ought to be working not in the world of ordinary commutative rings, but in the world of topological commutative rings. So let's consider this situation.
So this universal topological ring you get by doing that is the homotopy type of what?
Of a
I mean, so you
so pi 0 is C adjoin. Pi 0 and pi 1 both look like C adjoin x.
So you told us that, so I can see why you'd want to adjoin those two arcs.
Yes.
And so you change the homotopy type of your set, your space.
Mm-hmm.
You said that you could build a ring that contains this extension.
Yes.
Does that larger extension affect the homotopy type?
Yes.
Could you repeat the question, please?
Oh, I'm sorry. So the question is, what is the homotopy type of the object that I get when I do this massive construction of adjoining these two paths and then taking the free commutative algebra that they generate? And the answer is that the homotopy type is not as bad as you might think. So let's give this thing a name. So this maps to R by sort of sending y to 0 twice. So R is this topological commutative ring that's obtained by adjoining those two paths. What do you get? Well, pi 0 of R is just the ordinary commutative ring that you would get by dividing out by y twice, or dividing out by y once, equivalently. So this ring just looks like C adjoin x. Pi 1 of R, well, there's a canonical element in pi 1 of R, which is given, we have now two paths from y to 0, so we have a non-trivial loop from 0 to itself. But pi 1 of R is also a module over pi 0 of R in a natural way. So if I let epsilon denote that natural path that we can write down, it turns out that pi 1 of R is a free C adjoin x module on the element epsilon. And there are no higher homotopy groups above 1. So even though it looks like we did a completely horrendous construction, and even though we can't get our hands on this thing geometrically at all, for a homotopy theorist, this is not bad at all. This is a very simple space which has a bunch of connected components, and each connected component has only pi 1, no higher homotopy groups. So let me return now to this formula over here, and let's try thinking about what would happen if instead of taking the tensor product in the world of ordinary commutative rings, we took the tensor product in the world of topological commutative rings. So consider the ring of functions on the curve C. The ring of functions on the curve C prime and the ring of functions on the, or they're not curves actually, they're varieties of higher dimensions, A and B, sorry, and take their tensor product over the ring of functions on projective space of dimension A plus B. Now, I'm going to think of these things as ordinary commutative rings regarded as having the discrete topology, but I'm going to use the right notion of tensor product construction in the world of topological commutative rings. So this is something that a lot of algebraists would denote by putting a little L above the tensor product sign. The reason is this is the left-derived functor of the tensor product operation. Now usually those left-derived functors are done in the context of homological algebra. So you imagine that these guys are modules over, over this ring, and then you perform some kind of construction which involves resolving these modules by free modules. But it turns out that this construction is equivalent to doing some kind of construction in the world of topological modules. And you can just as well work in the world of topological modules that happen to have ring structures. And that's a little different from the usual homological algebra because the category of algebras over this ring is not an additive category. You can't add morphisms together. So this is what some people call nonabelian homological algebra, or what some people call homotopical algebra. It's something that very much has a flavor of homotopy theory in it. But anyway, what I want to say is that if you take the tensor product in this world of topological commutative rings, you get a topological commutative ring which I'm going to call R. And now what does R look like? Well, once again, so let me erase this to avoid confusion. So now let's contemplate this ring R. Well, first of all, if we just look at the level of connected components, if we forget that we're working in the world of topological commutative rings, then we just get what we would expect from ordinary algebra. We just get the naive tensor product of OC with OC prime over O of projective space. And now you might guess what happens. The ith homotopy group of the ring R is exactly what appears as the ith correction in Serre's intersection formula. It can be identified with tor I of OC with itself, with OC prime over O of projective space. So working in this world of topological commutative rings really solves the problem that I mentioned earlier, that the higher terms in Serre's intersection formula cannot be interpreted as invariants of the intersection of C with C prime. To solve this problem, what we have to do is intersect C with C prime in a more sophisticated version of algebraic geometry where commutative rings have been replaced by topological commutative rings. So let me give a few definitions to make you a little bit more comfortable with this world, and then state a generalization of Bezout's theorem, which will make it look very nice. So suppose that R is a topological commutative ring. So what does that mean? Well, first of all, we can make an ordinary commutative ring by collapsing all of the path components of R to a point. Pi 0 of R is just a commutative ring in ordinary algebra. And what I want you to think is that pi 0 of R is the underlying commutative ring of R. The difference between R and pi 0 of R as a discrete ring is that R might also have some higher homotopy groups. And those higher homotopy groups might carry some interesting information. That's sort of the whole point of this business. But somehow, pi 0 contains the most interesting or the most fundamental information. So how are we going to do algebraic geometry with these topological commutative rings? Well, let me review for you the definition of a scheme. This is the most basic definition in algebraic geometry, and then explain how to generalize it by inserting topological commutative rings. So, definition, a scheme is a topological space X with a sheaf of rings OX such that the pair XOX locally looks like spec A, O spec A, where here A is a commutative ring. So what's the derived algebraic geometry version of this definition? Well, we insert the word derived before scheme. And now everywhere that we see the notion of commutative rings appearing, we replace them by topological commutative rings. So there are a lot of things to remark on here. One of them is you have to ask what I exactly mean by a sheaf of topological commutative rings, because it's not what you might think, interpreting that most literally. But let me just comment on what's most important, which is how do I take spec A, O spec A, when A is a topological commutative ring and not an ordinary commutative ring? And the answer is it's not nearly as bad as you might think. So let A be a topological commutative ring. Then spec A, as a topological space, is just defined to be spec of pi naught of A, the spec of the underlying ring. So let me remind you, that's the set of prime ideals in the ordinary ring pi naught of A. And moreover, we're going to give spec A its usual topology, the Zariski topology. And you recall that the Zariski topology has a basis of open sets, U sub f, namely the set of prime ideals which do not contain the element f. And here f is allowed to be anything that lives in pi naught of A. So as topological spaces, these derived schemes are just like schemes. They look like Zariski spectra of rings. What's different? Well, what's different is the structure sheaf. It's no longer a sheaf of commutative rings. It's now a sheaf of topological commutative rings. But it's not very different. If you consider O spec A on one of these open sets U sub f, well, if this was ordinary algebraic geometry, I would just take the ring A and invert the element f. And now let me simply remark that this is a construction which makes perfectly good sense in the world of topological commutative rings. There's a good construction for inverting an element. So this gives the definition of a derived scheme. What does a derived scheme look like? Well, locally, it just looks like an ordinary scheme. The only difference is that its structure sheaf has some higher homotopy groups, which are carrying some kind of mysterious extra information. And the extra information that they're carrying is precisely the information that you need to extract the higher terms in Serre's intersection formula. So what happens now? Well, so what should I call this? Improved Bezout's theorem. You can extract a version of Bezout's theorem which has essentially no hypotheses. Suppose that we have two smooth varieties in a projective space, any dimensions that you like. Well, their intersection doesn't have to be smooth. And in the case when the intersection is is bad, you really have to intersect them in this world of derived schemes, not in the world of ordinary schemes. And you also have to jazz up what you mean by the fundamental class of such an intersection. So there's a generalization of the theory of fundamental classes to this world of derived schemes, and the things which you obtain are usually called virtual fundamental classes. So you have to interpret this in the sense of virtual fundamental classes, but provided that you do that, this formula is valid with essentially no hypotheses on the way that C and C prime intersect. They don't have to intersect transversely. They don't have to even intersect in the right dimension. C and C prime can coincide for all you care. If C equals C prime, then this thing interpreted classically is certainly not going to give you the right answer. But as we saw earlier, this derived algebraic geometry working with topological commutative rings knows the difference between imposing the defining equations of C once and imposing them multiple times. So this idea of derived algebraic geometry has several applications. This improved Bezout's theorem is only one of them. And the applications run in both directions. So here's an application of homotopy theory to algebraic geometry. That is, if we inject these ideas from homotopy theory, we can extract out better versions of some classical theorems in algebraic geometry. And in my lecture tomorrow, I'll be talking about some applications which run in the other direction, namely applying ideas from algebraic geometry, enriched in a suitable sense, to prove things about homotopy theory. So that's about all I have to say. I thank you for listening to me.
Questions?
So you use the term virtual fundamental class. So this term in algebraic geometry has a very precise meaning in deformation theory. So does it have anything to do with your concept?
Yes.
Could you please
Is this exactly the
Sorry, the question is whether or not the virtual fundamental class.
class of C intersection C prime.
Yes.
So what do you mean by that?
Well,
So typically what that, so for instance, well, the example we all know, so most of us know, Gromov-Witten's theory, right? When there's certain spaces on which you want to do intersection theory, they have an expected dimension, but they don't have the actual dimension, but you can still do enumerative geometry as if they had the expected dimension.
So the question is, to what extent do the virtual fundamental classes that I've mentioned agree with the notion of virtual fundamental class as it exists in, for example, Gromov-Witten theory? And the answer is that they're the same notion, that these spaces that appear in Gromov-Witten theory that do not have the expected dimension actually are the underlying schemes of certain natural derived schemes that you get by thinking about the problem in the world of derived algebraic geometry, and that the virtual fundamental classes that appear in Gromov-Witten theory are precisely the same virtual fundamental classes that appear when you go through the process that I have not described.
Other questions? I'd like to thank Jacob again.